A relative min could look like that, or it could look like that. This is not new information for anybody in the room. We're okay? Now, what if you were asked to show that a function had a relative maximum? What would you look for? How would you show it? I see rum beer. That's it. Relative max. How do you show relative max? One person, two, maybe three, four. Jen, how do you find relative max?
F prime will change from positive to negative.
Okay, F has a relative max if F prime changes from positive to negative at x equals c. That's one way that we show relative max, and there's another way. What's the other way? F prime changes, but F changes. What's the change in F for a relative max? No, what do you mean?
From increasing to decreasing.
F of x, the original function, makes a change from increasing to decreasing at x equals c. Right, this is what we've done before. This is just meant to be a review. Okay, so Edgar, if I said local minimum or relative minimum, how would you show relative minimum?
F prime changes from negative to positive.
F prime of x changes from negative to positive at x equals c. And Jonathan, what's the other way you could show relative minimum? F of x makes a change from decreasing to increasing at x equals c. Total review, we've been here before. Some textbooks, in addition to saying relative max, they also use the word local. So a local maximum is the same thing as a relative maximum. A local minimum is the same thing as a relative minimum. We're good? Good. All right, so new vocabulary word coming here. The word is absolute max. Absolute max.
Absolute max.
The word absolute, if it is the absolute maximum point on the graph, the implication is it's the highest point. That's all. We're not, if I talk about absolute max, I'm not talking about a change in behavior from increasing to decreasing. I'm talking about the highest point on the graph. Okay? So that's what we're going to talk about with absolute max. If you have an or I guess in this case absolute min, so awkward. The function f has an absolute minimum if f of x is at its lowest point at x equals c. So absolute minimum is just the lowest point on the graph. That's that. But it has to be a point. So to be an absolute max, f of x is at its highest point. Any questions about absolute max or absolute min? Does this just basically make sense?
Yeah.
Right, like this is how you would define it. Absolute max, it is the highest point. Absolute minimum, it's the lowest point. Now, some textbooks, because they want to get a little bit fancier, what they're going to say for absolute min, they're going to say that f of c is less than or equal to f of x. So you have the lowest point at x equals c if f of c, the y value, is less than or equal to f of x for all x in the domain of f. So the y value at this special value of c is less than or equal to all the other y values. It's the smallest of all your y values. Over here we would say f of c is greater than or equal to f of x for all x in the domain. Okay. Something that I want to make really super clear about absolute max and absolute min. Absolute max is the highest point. I want to emphasize that. It's the highest point. You might want to underline this word point or draw some attention to it. If we're saying that you have an absolute minimum, it actually has to be a point on the graph. There has to be like a point there. So we're not going to include the infinities because there's not a point where the y value is equal to infinity. And we're not going to include negative infinity because there's not a point down there at negative infinity. We're looking for the highest point and we're looking for the lowest point. So real quick, turn to somebody near you. Explain to them the difference between relative max and absolute max. What's the difference?
I thought both of them were. I think it's not limited to be any maximum
She was getting near point. She was not. Yeah, she was.
Okay, Jen. Oh, God, I love that question. Can you ask that question one more time?
Can you put the same thing at the same time?
The question sounded better when I was over here. It got really generic over here. Can it be the same thing at the same time? What do you mean by the same thing at the same time?
Could it be a relative max and an absolute max?
So can a function have a relative max and an absolute max at the same time? Can anybody think of an example of a function that has an absolute max and a relative max at the same time? Can you guys show me relative max again? Relative max, like this, or the cusp point. And absolute max means the highest point. Can anybody think of a graph that has a relative max that's also an absolute max? I need relative max and at the same point absolute max. I see Rambeer who thinks he's got an example. How about all the other nifty brains in the room? Absolute max. I see a lot of people looking at absolute min. The graph of the absolute value of x would be a horrible example of a function that has a relative max and an absolute max at the same time. Horrible example. But a good example would be, how about the negative of the absolute value of x? Does this count as a relative max?
Yes.
Because I'm changing from increasing to decreasing, does this count as absolute max?
Yes.
Yes, good. So, 3 minutes, time to draw. What I want you guys to do, there are 5 situations down here at the bottom. I want you to partner up with somebody, and I want you to give me a sketch of a function that satisfies those conditions. I'm not worried about the... I should be worried about that. I'm not worried about the name of the function. I'm not worried about the equation. I want a sketch
Say hi, Jenny.
of a function that satisfies those conditions. Yes, sir.
That's Jenny.
Is this like a graph or this? Is this allowed to do with relative max? I mean, not the relative max, but absolute.
We'll talk about that.
I gotta be so.
A function that has the relative minimum, which is also an absolute minimum.
Wait, so I don't get what we're writing. Like, what are we actually?
We're drawing.
So when this is like.
Negative. He said negative absolute.
Remember,
No,
do
wait,
not
that's
worry
next.
about the equation. I want a graph.
The other way.
Woohoo!
You're right.
Function which has both. So basically the same.
Oh, it's
2 more minutes.
Absolute maximum and the absolute.
But no absolute. Relative max.
Ah.
A function which is an absolute maximum.
It's just the middle.
Wait.
This and an absolute minimum.
Oh, I didn't see that.
You gotta be
Relative maximum, which is not oh.
Relative maximum,
Well, it didn't say it couldn't have a
which is not the absolute max. So it's a
Wait, for number 3, where did you draw that?
because it's just an absolute maximum, so it has a point, but there's no absolute minimum, so you don't draw another little point.
I see what you're saying.
A function which is the function which does not have an absolute maximum.
Yeah, I agree.
It's not an absolute minimum. So it's a relative maximum and a relative minimum. Is it too late?
Okay, 30 seconds to lock them in.
Mr. D, I didn't know we didn't have school next week. Oh, that's why I didn't tell you because my plans. That's why I was thinking about. He was like, "Eh."
That's the cosine?
I don't care.
What did you draw for the last one? I drew that one for this.
I'm gonna borrow Chris.
That's
All right, so Christian has been voluntold here. We got a function that has a relative minimum, which is also an absolute minimum. Does this work?
See.
Right, relative minimum because I'm going for the function changes from decreasing to increasing. Absolute minimum because lowest points. Done. Just some definitions. A function which has both an absolute maximum and an absolute minimum. So if this function has an absolute maximum, that must be like this guy over here. Right, absolute minimum over here. Now, what if the function did that? Where's the absolute maximum now? No, Amy, where's the absolute maximum now?
It's still at the same points because it can't be like a negative or positive thing.
Okay, so you would say that this is still the absolute maximum? How many guys would agree with that this is still the absolute maximum? Go back to your definition of absolute maximum. Go back to the definition of absolute maximum. What did I say about absolute maximum? It's the highest point. So Noemi, could this be the absolute maximum? Is that the absolute highest point on the graph? Are there any points that are higher? Yes, so this can't be the absolute maximum. In fact, so like this guy's the absolute maximum?
No, infinity.
This guy?
Point, the arrow.
It doesn't have one.
There is no absolute maximum in that case because the absolute maximum has to be a point. Okay, so we want to be really careful with that one. Function which has an absolute maximum but no absolute minimum. Love it. Highest point, no lowest point because the arrows are going down forever. No lowest point. Great job. A relative maximum which is not the absolute maximum. Here's the relative maximum. The absolute maximum is where? Where's the absolute maximum? Jose, what'd you say? It doesn't have one. Why?
Because there's a point.
There has to be a point. There is no point where you have a highest point. So you want to be careful with these things. A function which does not have an absolute maximum and does not have an absolute minimum. Oh, that's not a blank. That was your example of a horizontal line. Perfect. Love it. No problem. Well done. All right, let's keep going, shall we? So one of the things that's going to be really important is I'm going to start having to put blinders on you. So like, I'm not actually going to do that. That's probably illegal in some places. We're going to start talking about absolute max and absolute min on a restricted domain. So for this graph over here, this is the graph of x cubed and some stuff. I want you to look on the interval -2 to 4. So if I put my blinders on, if I only look from x equals -2 to x equals +4, my first question is there a relative maximum? If I only look between -2 and 4, Abraham, where's the relative maximum?
Where x equals 4 point something.
Wait, between -2 and +4, I want to focus on the adjective in front. Relative max.
0.
Okay, but I want coordinates.
Oh, x equals 0 and y equals 0.
X equals 0, y equals 0. And Eunice, is there a relative minimum on the interval -2 to 4? Where's that going to be? 2, -4. Anthony, is there an absolute maximum on this interval?
4.16.
One more time.
4.16.
4, 16, because that's the highest point, right? And Jasmine, is there an absolute minimum?
Yes.
Where?
At -2,
-2, what is that, -20? Okay, so sometimes we're going to talk about absolute max and absolute min on a domain, like with a domain restriction. So you're going to put your blinders on. So just take a couple of minutes, finish this off on the interval -2 to 1, on the half open interval -infinity to 2, on the full open interval -infinity to infinity. We'll talk in about 2 minutes. Careful attention to those domain restrictions. Alright, why don't you compare your work with somebody near you, have any conversation about any disagreements that you get, and then I'll put my answers up there with that.
Say hi, Jenny. Hello. For these two,
I got, okay, so I got
yeah, I got this one too.
this for the maximum, since it was just on -2 and 1. I thought that's oh, that's the only maximum. Oh, that's the height.
None.
Zero. 2, none for both of these, because I was like, since it goes to infinity, there's like no point.
Alright, let's see. Well, you guys did. So, second row, on the interval -2 to 1, you've got a relative minimum at 0, 0. You have no relative minimum. You have an absolute max at 0, 0, and an absolute min at -2, 20. How many of you guys get the whole row right? We're pretty right. This should just be like very like basic definitions. Okay, on the open interval negative infinity to 2, relative max at 0, 0, there is no relative min. Absolute max at 0, 0, no absolute minimum. I want to avoid using the dash or the NA or the made-up notation DNA.
Does not. Oh.
I think this person meant DNE for does not exist. DNA, that's a different class. No one wants to do 9th grade over again.
True.
Nobody. Last row, from negative infinity to infinity.
And beyond.
0, 0, to negative 4. There is no absolute maximum. Marked here. Why is there no absolute maximum? If I go from negative infinity to infinity, why is there no absolute maximum? Because the function keeps increasing, because there is no... There is no highest point. I could not have said it better myself, even though I had to. All right, Mariah, and why is there no absolute minimum on negative infinity to infinity?
Because there's no absolute lowest.
Because there's no lowest point. Is everybody like, oh my God, we've got this under control? This has nothing to do with like big brain calculus. This is just some definitions. Wake up, son, it's okay. There's only 191 days left to the AP exam. Now it's time for some stuff. I know it's wrong. Move on. Oh, so excited. So now we get, the next 30 minutes is like real calculus. Your brain will hurt within the next 10 to 15 minutes, or else I'm not doing this right. So, I've got a new theorem with a name. I did not make this up myself. If I did make it up myself, I would name it after myself. This new theorem is called the extreme value theorem. We've experienced other named theorems, namely
Indeterminate value.
the IVT, the intermediate value theorem, not the indeterminate value theorem, the intermediate value theorem. The extreme value theorem says this: if f is a continuous function, no holes, no jumps, no breaks, no vertical asymptotes, on a closed interval AB, closed interval, then f must have, this is a must, have an absolute max and an absolute min. Continuous function on a closed interval, there will always be an absolute max, there will always be an absolute min. Why don't you draw on your paper somewhere a continuous function? And then put your blinders on. Okay, so I'm gonna put, I don't know, here's my function. Okay, here's my function f of x, which is continuous. Here are my blinders. Here's x equals a, here's x equals b. For that function in that interval, is there an absolute maximum? Where? Over here, right? For this particular example, the maximum happened over here. This is going to be the absolute max. Okay? Do I have an absolute minimum? Right? Kind of like this guy over here, probably. So I'm curious, did anybody come up with a function that didn't have an absolute max or didn't have an absolute min? You think you got one? Can I see it? You didn't draw it. Could you draw it for me? Did anybody else come up with a function that doesn't have an absolute max or an absolute min? We're about to rip Abraham's paper apart.
That does not.
Oh, so many reasons to rip this one apart. Okay, but we're gonna reward bravery here. Okay. All right. We need some kindness coming towards Abraham. First mistake. What's the first? Everyone's just laughing at him and no one's actually telling him. Mean.
I don't know.
Mean. Margier is over there. Marvin?
That's not y.
This is not y equals x. Y equals x, you may remember, is that line that passes through the origin. This could be
He's close.
y equals 1. Okay? But that's all right. You've got a horizontal line. Does this have an absolute max?
No. There's no one highest point.
It's just 1.2.
So first of all, the extreme value theorem says on a closed interval. So I've got to put my blinders on. Is there a point that is greater than or equal to all the other ones? One more time. Is there a point that is greater than or equal to?
Yes.
Could be this one. This one. This one. Any point for this particular function on this interval counts as the absolute maximum. Is there an absolute minimum? Is there a point that is less than or equal to all the other points? Really, any of them. So great example, if only you had named it well. Even this linear function has an absolute maximum and it has an absolute minimum. According to the extreme value theorem, there is always an absolute maximum and there is always an absolute minimum. Okay, so my graph over here, the absolute max happened at the endpoint, the absolute minimum happened inside the interval. Okay? All right, that didn't go as well as I wanted to, but maybe we'll stick the landing here. I need two actors, two folks that are really inspired to act. Inspired to act. And you can read the lines that are on the paper.
I don't got my acting.
Jennifer, you're gonna come on up and do it?
If he does it.
You'll do it if he does it. We've got some positive peer pressure happening here.
Let's do it.
All right, come on up. Jennifer, you are going to be the mighty maverick. Edgar, you are going to be the wise wizard.
Why'd you
Okay?
give him the wizard? That's right.
Mighty maverick,
It's self-easy.
You're not friends.
wise wizard. Wise wizard, take it away. Lights, camera, action.
Oh wait, I have to read this? Wait, read
Oh, dear
it.
God.
Take two.
Take two.
Okay, I get it. There are absolute extrema and relative extrema. But what's the big deal?
Well, I was chatting with Mr. D last night. He said that a lot of the problems we are going to study in the coming weeks will involve domain restrictions.
And I care why.
Well, with these domain restrictions, we always need to check the endpoints. Sometimes the relative maximum and minimum points won't even be in the interval we are restricted to.
Alright, I'll be sure to check the endpoints. After all, I do want to do well on the AP exam.
That's the spirit.
Hey, I noticed that the extreme value theorem says that the function has to be continuous on a closed interval. Do you think it makes a difference if the interval is open or half open?
I have no idea. Let's ask Mr. D. He knows everything.
God, I love that part. Well done, bravo.
Oh, you just let the camera move.
Oh, all right. I want you to have a conversation with your partner, please. Note number
Oh, you
one.
see Jenny again.
Why is that function there
There she goes.
not a counterexample? The extreme value theorem says if you have a continuous function on a closed interval, there is always an absolute max, and there is always an absolute min. I want you to examine this function on this interval and decide if you can use the extreme value theorem. The quietest
I never have it
conversation
on.
ever heard in my life.
I never have it.
Why are you scared of talking now, Jose?
Because I haven't gone with
What do you?
Can you use the extreme value theorem for this function on this interval? Oh my gosh, all these people that have forgotten what the graph looks like, Martyr, thank you for reaching for your resources and graphing it on the calculator. I hope you then realize, wow, I'm supposed to know this one.
I'm worried about applying the knowledge.
True.
Let's see. The function must be continuous.
A thing in the middle. Oh my god. Oh my god. It gets even worse the more I listen to you, Jose.
A thing in the middle?
A thing in the middle. There's the graph of f of x equals 1 over x. The
There we
question
go.
for you, Daisy, is this. Can we use the extreme value theorem with this function on the interval x equals -1, x equals +1? Can we use it? That's the question for you, Daisy.
Yes,
Okay. Why?
because it has the absolute maximum and the absolute minimum.
So you see an absolute maximum somewhere and you see an absolute minimum. Where do you see an absolute max?
At is it at the? I'm not sure.
Okay, so my question to you, but really for everybody in the room, can we use the extreme value theorem here?
Yes.
Go back to the extreme value theorem. All these named theorems have conditions. Daisy, can I come back to you on this one? Can we use the extreme value theorem here?
No,
Because
because it's not continuous.
not a continuous function. F of x equals 1 over x is not continuous. Now, be careful. It's not continuous on the interval -1 to 1 because why? What's the thing? If you say horizontal asymptote, it's going to go badly for you. Because of a vertical asymptote at x equals 0. So, can I use the extreme value theorem? No. No. Now, Daisy, you said you saw an absolute maximum and you saw an absolute minimum, right? So, can somebody tell me what was the mistake that she made? What's the mistake? What's the mistake? There's a mistake here. Anthony, do you see the mistake? One more time. The function's not continuous. That's part of the mistake. But she saw an absolute maximum like over here. So what's the mistake? Those are the infinities, and an absolute maximum must be a point. Okay, all those definitions that we were talking about a little bit ago, they're important. Okay? So the second one, I want to know, can you apply the extreme value theorem to the function 1 over x on this interval 1/2 to infinity? Have that conversation. F of x equals 1 over x on the interval 1/2 to infinity. Do we get the EVT?
Isn't it? Here, I'll put it on Jasmine, and then they can just hear us talk. Say hi to Jasmine.
If you can use the extreme value theorem, it's because you have a continuous function on a closed interval.
It's on YouTube. Everybody watching. I don't think so because I mean, like all our other stuff for infinities, like they didn't exist. So like,
Absolute maximum.
negative 1/2. It's continuous, but it's not a point because of the infinity.
Yeah.
Right?
So there won't be
So it doesn't apply either.
All right, folks, let's pull this together. Can we use the extreme value theorem?
No.
If you can use the extreme value theorem, it satisfies two conditions. Number one, continuous. Is this function continuous on the interval that I care about? Right, vertical asymptote's happening over here. But the second condition is closed interval. It has a definite start and a definite end. This one doesn't have a definite end. Is there an absolute max?
No.
Look at the graph. Adriana, where's the absolute max?
Absolute max would be at x equals 1/2.
Right over here is your absolute max. Right, would you guys agree? That's the highest point. You can see this. Where's the absolute minimum? There is none. Right? Because, as Jose was saying oh so nicely, this graph has a horizontal asymptote. I'm going to get closer, 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 closer to y equals 0. But closer doesn't mean that you got there. There's no lowest point because no matter how far I go out, I can get a little bit lower. Are we okay? All right, good. So, extreme value theorem, 2 conditions. Tell your neighbor what they are.
That's the absolute minimum.
Continuous and.
Or a close interval.
Not or, continuous and. All right. Extreme value theorem. You have to have a continuous function and closed interval, a definite start and a definite end. If you have both of those things, the promise, the guarantee is you will have a highest point and you will have a lowest point. We're okay? All right, so wherever you drew your graph, right, I'm just going to add mine over here. The absolute maximum, the absolute extrema can happen in one of 2 places. So if I'm looking for an absolute extrema, the 2 places I look, number 1, I look at the endpoints. I look at those endpoints on the interval. Like in this case, the absolute maximum happened all the way over to the right. For anybody on their graph, did anybody have the absolute max like all the way over to the left? Like maybe your function started high and then it decreased? Nobody did. Okay, could that happen? Could you have the absolute max on this side? Okay, so the first place you look is you look at your endpoints. The second place, I'm going to call these are your internal candidates. The internal candidates is a point like this guy over here, your absolute minimum. In my case, it happens on the inside. That absolute minimum is an internal candidate, and the way we're going to find it, we're going to look to see where does the function equal 0, or where is the function undefined. So our process for going after these absolute extrema, we're going to check our endpoints, because that's where they could exist, or we're going to check an internal candidate. And this is where we're finally going to get to do some really good calculus stuff. So excited. Oh gosh, so excited. All right, so let's flip it over one more time. All right, we're going to, if all goes well, we'll get through both of these, but at the very least, I want to get through one of these and do it well. All right. And tonight's homework, you're going to get a couple of these to practice and perfect this skill. Christian, don't let me erase this. Okay. Thank you. All right. I want to determine the absolute maximum and absolute minimum values for this function on a closed interval -1 to 8. I've given you a function. I've given you a closed interval. Does there have to be an absolute max?
Yes.
Does there have to be an absolute minimum?
Yes.
How many would say yes, there has to be an absolute max and an absolute minimum? Okay. Eunice, why?
Because that's one of the conditions.
Wait, what's one of the conditions?
So, use the extreme value theorem.
The extreme value theorem, the conditions. I'm so glad you used the word conditions. What were the conditions? There were 2 conditions.
Has to be continuous.
The function has to be continuous, and you have to have
Closed interval.
a closed interval. There's one of those you should be comfortable with.
Continuous.
I know I've got a closed interval. The continuity of this function might be a little tricky for us to figure out. Eunice, you okay with that? So the conditions are continuity and closed interval. The guarantee of the extreme value theorem, what's the promise? If the conditions are met, the promise is, Anthony, what's the promise? There will be a global max, there will be a global min if you've got both of the conditions met. So here's where we're going to start. We're going to start with this function f of x equals x minus 4 times the square root of x plus 1. And I've never done this before, but we can do it if you want to. is number one, we're going to check the endpoints. Meaning I'm going to find f of negative 1, and I'm going to find f of 8. I've never actually presented it this way. I'm curious to see if you guys like it this way better. So first, check the endpoints. Check the value of the function at the endpoints. What did I really just say?
Plug in.
Plug in. Plug in. So this is going to be negative 1 minus 4 times the square root of negative 1 plus 1. That's what, 0. Square root of 0 is 0. I think I've got negative 1. F of 8 is 8 minus 4 times the square root of 8 plus 1. 8 plus 1 is 9. Square root of 9 is 3. I think we've got negative 4. Those are the endpoints of the function. Now, it's possible that one of these is the absolute max and one of them is the absolute min. Possible, but it doesn't mean has to be. So the thing that we go for next are your internal candidates. The way that we're going to find the internal candidates is that we're first going to find the derivative. Because what I'm looking for are those relative max and relative mins. So take a moment. Show me how good your derivative skills still are, even though we've been away for a couple of days. It feels like forever. Feels like August all over again. X minus 4 times the square root of x plus 1. So 1 minus 4 times, I need the derivative of the square root of x plus 1. Which is 1 over 2 times the square root of x plus 1 times the derivative of the inside, which is 1. How many guys honestly had that as your derivative? Okay, chain rule skills are good. The reason that you found, round beer, what?
Why is it that you kept the negative 4? I thought that's a constant.
It's a constant that you're multiplying by. If this was x minus 4 times x squared, what would the derivative be?
X minus 4 times x squared.
If it, imagine this is x squared here.
Okay.
It would be 1 minus
4x.
4 times 2x, right? The 4 doesn't become a 0 because you're multiplying by it. All right, that's the derivative. Here's the thing though. The reason that you're finding the derivative is you're going after these internal candidates. You're looking for where you might have an absolute max or an absolute min. So what you're going to have to do is two things. One, you're going to figure out where is this derivative equal to 0. You've survived the calculus, it's just going to be some algebra. The second thing is you've got to look at f prime of x equals 1 minus 4 times 1 over 2 square roots of x plus 1 and figure out where does this not exist. Let's tackle this guy here. If I clean this up a little bit, 4 times 1 over that times 1, well that's the same as 4 over 2 times the square root of x plus 1 is equal to 0. I don't know if we've had this conversation, but back in high school when I was running in the gangs, when I was in the streets, true story, I was in the gang. I had a name,
What's your name?
Fraction Killer.
Oh my
Because I knew with a killer, that's right, because I was from Massachusetts, I knew that the best way to solve equations that had fractions was to multiply by the common denominator. Let me say that again so you guys can join my gang. I know you guys used to be right-hand rulers, but that's over.
Should be my right.
I'm going to multiply this equation by the common denominator. I'm going to multiply by this 2 times the square root of x plus 1. Stay with me. Here's why it's so awesome. Distribute this through. 2 times the square root of x plus 1 times 1 is 2 times the square root of x plus 1. Minus this guy here times 4 over 2 square roots of x plus 1. all of this times this guy here.
2x plus 1.
I've got 4 over 2 square roots of x plus 1 times 2 square roots of x plus 1. So the 2's cancel. The square roots of x plus 1 cancel, and I'm left with 4. That should be wicked easy for everybody in here to solve. What are we going to do?
Add 4.
I can add 4 to both sides. That's good. I'm going to divide by 2. I can square both sides. And I can solve for x. And I'm going to get x is equal to 3. X equals 5? Is everybody okay with x equals 3? X equals 3 is your candidate. It's where you're going to look for an absolute max or an absolute min. But I also have to figure out where is f prime of x undefined. Look at that derivative. Where is that undefined? Is there any value, I see you're on here, hold on a little bit. Is there any value where the derivative is undefined? And the place where I'm really going to check, I'm going to check the denominator. Right? If this whole expression is going to be undefined, it's going to be because 2 times the square root of x plus 1 is equal to 0. Divide both sides by 2. Square both sides.
That's not your final answer.
Right, these are not the answers. These guys here are your candidates. The way I'm going to make the decision about which one's the absolute maximum and which one's the absolute minimum, trust your instincts. What are you going to do? Adriana, what are you going to do?
You're going to plug those x values.
All I need to know is to figure out which one gives me the biggest y value and which one gives me the smallest y value. Just plug them back into the original. So I'm going to find f of negative 1. Hey, I think we already did that, right? F of negative 1 is negative 1. And the other one, f of 3, is 3 minus 4 times the square root of 3 plus 1. 3 plus 1 is 4.
2.
Square root of 4 is 2. 4 times 2 is 8. Negative 5. Your absolute maximum will either be an endpoint or one of the internal candidates. Where's the absolute max? Where's the absolute max? Where is the biggest y value? Right, this guy here is your absolute max. Where's that absolute min? Right, the absolute min, the smallest y value that you've seen is right here. Absolute min. So to recap the process, if you're given a function and you want to find the absolute max and the absolute min, evaluate the endpoints. Find the derivative. Figure out where the derivative is equal to 0, because that could be a relative min or a relative max. Find out where the derivative is undefined and evaluate the function. Remember,
We look for the undefined point just in case the original function is a cusp.
because you could have a cusp point, right? The absolute value graph. Okay? All right, so why don't you guys get started on number 2. You're not going to have much of an opportunity to go too far. I'll leave this up here for you to compare your work to. Tonight's homework is on the next page and the instructions are pretty clear.